The term procedural audio is used to characterize a procedural, systematic, or algorithmic approach to generating audio. The phrase is often used to describe a spectrum of approaches applied to game audio implementation. This ranges from what Stevens and Rabel refer to as procedural sound design, where pre-existing audio assets are rearranged, combined, or manipulated. On the other side sits the definition of procedural audio provided by Farnell, referring to an algorithmic approach to real-time synthesis. In either case, the intended result is that the systems of audio in use provide a greater variety of outcomes, reducing unwanted repetition, and offer a more responsive solution to balancing the functional integrity of audio and the player's autonomy. This project aims to further explore the potential benefits and limitations of procedural audio for games, examining the broader question of how these models can address the gap between realism and the subjective nature of artistic interpretation, arguably inherent within the practice of sound design. Specifically, the project focuses on how the coupling of granular-based synthesis and particle systems may achieve this. A granular-based procedural audio model has been developed using the object-based programming language PD and compiled using the browser-based service Heavy by NZN Audio. The plugin has been integrated with and mapped to a modular particle system in the game engine Unity. The final model has been tested against other audio implementation techniques as part of an interactive listening test. The test was designed to assess the comparative believability of the systems in use within the context of a virtual environment. The project intends to present the potential of this granular-based model, along with its noted limitations, so that it may be further developed as a practical, real-time tool for sound designers and game audio engineers. In video game design, solid objects are usually represented by 3D meshes or 2D sprites, while particle systems are used to generate fluid and intangible phenomena such as fire, smoke, or water. A single particle is made up of a small image or mesh, which represents a portion of this amorphous entity. The particle system then generates large numbers of particles to create the effect of an entire entity. Game engines such as Unity and the Unreal Engine employ a modular approach where the user can control and parameterize numerous behavioral and physical aspects of the particle system, such as size, velocity, and their spawn rate. These parameters can also be randomized or set to develop over a particle's lifetime. Granular approaches to synthesis were initially developed around physicist Dennis Gaber's theory of quantum sound. Gaber's theory suggests that sound is made up of quantum-sized individual sonic particles, or acoustical quanta, as he called them. Granular synthesis is the process of deconstructing a sound into a large number of very short individual audio grains, or sonic particles. A new sound or acoustical event is created by rearranging and recombining these audio grains. The duration of these audio grains typically lasts between 1 to 50 milliseconds, though can vary outside of this. The number of audio grains or density varies depending on the model, but can range up to thousands per second. Early implementations of granular models were developed by Rhodes and Tro, both inspired by compositional works by Iannis Xenakis. Xenakis' first works using granular synthesis techniques were created by splicing magnetic tape into tiny segments, rearranging the segments, and taping the new arrangement together. When a single particle emitted from the particle system hits the attached collider, an individual audio grain is triggered. Physical data from the particle, including its size, velocity, expended lifetime, and remaining lifetime, is collected and sent to the granular model. Processes within the model then map this data to the pitch, envelope amplitude, attack, and decay of the individual audio grain. When multiple particles are emitted, hitting the collider, this results in a stream of audio grains being triggered, with the parameters of each grain mapped to a specific particle. These grains are essentially layered and cross-faded together to form a continuous audio texture, sharing approximate behaviors to the particle system. This allows users to load a pre-recorded audio file into the model, which is then deconstructed, manipulated, and rearranged to create a more appropriate and synchronous relationship between the audio and visual representation of the particle effect. Repetition is minimized, audio quality is kept to the standard of the recorded file, and any interaction or changes to the particle system will result in a direct and appropriate response from the accompanying audio. Two versions of the final model with differing source sample lengths have been implemented, alongside a physically inspired synthesis model, loop sample, concatenated sample, and two non-parameterized versions of the granular base model. An interactive listening test application has been developed, allowing independent assessors to rank the comparative believability of each system integrated with a fire-based particle effect. The parameterized granular-based model with a 10-second source sample scored consistently higher results than all other systems tested. The ratings for this model were statistically significant in comparison to the loop sample, concatenated sample, physically inspired model, and a non-parameterized granular base model with a 1.5 second source sample. Pairwise comparison suggests that the ratings were not significantly different to the parameterized granular base model with 1.5 second source sample or the non-parameterized model with the 10-second source sample. Both informal and formal interpretations of the results suggest that the granular-based approach has a positive effect on users' perception of believability. It should be noted, however, that this conclusion should not be interpreted as proof of the model's success over the other systems, only that the model's potential is sufficiently illustrated. It is recommended that the model be further developed and optimized according to the methods detailed in the dissertation, and that further testing is needed with a wider range of sound types, and preferably a larger sample size, before the proposed model could be considered ready for commercial use.